Okay, so we continue. Now you can download the slide. Hit it. It's like before we discuss the paper before. It's the system cascade analysis. Describe. We learn about last aspect, but this is the relative of it, which uh, which the author so modify or improve it or couple it with time-based pinch analysis. But mm, I want to focus. Yes. So this paper, the author is from UTM, case study. It's based on a local, I would say, the farmer located. So biogas decentralized energy systems and modern technology in developed country. Later they explain why we need to conduct this study. It's something to do with the policy. In developed countries, this is one of the energy efficient and eco-friendly technique for production of bioenergy disabling and to reduction of dispose mass building and greenhouse gases. So the aim for this study is to present a new numerical method. It's a gas system cascading analysis. Later we see when they start doing the initial iteration for the gas cap, then they will use this cascading. But the table for gas cap is simple, but to prepare the data for that table, it's not hard, but yeah, it's, it's a lot of work. So based on time-based pH analysis principle, Gesca is capable of targeting the biogas supply in chain as well as acting as the different product. Okay. So is capable of targeting the biogas supply demand chain as well as optimal capacity of anaerobic digestion and biogas storage system for unknown total demand profile with the consideration of energy conversion efficiency for different biogas quality, charging and discharging system and process. So what does it mean is instead of focusing on one demand, like we collect the biogas from this agriculture sector, instead of using it for one application like cooking gas, they might not might there can be several other applications. So this paper they do the optimization for electricity, for natural gas vehicle, NGV, and cooking gas. So they do it for three types of demand, but using one one gas cascade analysis. So far, what you have learned is we didn't actually combine several type of data. It's mostly like we have this plan and we have several processes. So we do the optimization based on the process. So for this case, the optimization is not on the process itself, but toward the demand each the cases case. But still, the optimization is based on that class that is by the correct word, the gas generation by the we can say poultry. In the illustrative case study, the optimal capacity of anaerobic digestion was 6 to 9 with initial energy content and maximum energy capacity of the gas storage of 737 and 16988. The simulation study also revealed that application of gas optimized biogas energy system could potentially reduce carbon emission up to 138 tons CO2 per day, CO2 equivalent per day. Moreover, a sensitivity analysis was conducted. Okay. Let's talk about what is biogas. So for what is biogas, we need to refer to the paper. It's page 101, this page. The biogas in Malaysia is derived from the anaerobic digestion of biomass feedstock. Common biomass feedstock comprises of organic fraction of municipal solid waste, SW, sewage, sludge, animal byproducts, as well as palm oil mill effluent, or mill. In the present situation, the recovery of biogas through anaerobic treatment of palm oil is more favorable in Malaysia, driven by the fifth entry point project EPP5. So this is why they do this project, because of this policy, National Key Economic Area or NKA program, which is intended to install biogas system in all palm oil in Malaysia by 2020. This paper is in 2017. Not sure if they achieve it or not. In order to support the EPP5 program, formulation of a comprehensive design framework for biogas-based distributed energy system would be imperative. The overall process for the biogas distributed energy system with illustration of multiple demand administration in figure 1. This is the process diagram. Let's start with the feedstock treatment, then into the aerobic digestion. So the gas is stored in the storage, and external biogas going into the storage. Sorry. Okay. Then we have the cleaning, meaning you turn it or boil it. Sorry. Burn it for the heating application. Also burn it for the electricity. What else? So upgraded is goes to the compressor, the gas become a clean gas, goes to the natural gas grid, compressor become vehicle fuel, NGV, natural gas vehicle. So in this case, we have four applications. So this paper is focusing on three applications: electricity, NGV, and cooking gas. So for TBPA, it's already used several other processes before this. If you refer to, okay, this like. So what of this TVPA design approach include the supply chain aggregate planning using pinch analysis or blend composite curve. So those who do exchanger heat optimization, they will use GCC. Some of colleague asking me. So for less pinch analysis, I still don't see people using GCC. So for meeting the demand of a specific type of maximum profit, yes. For power optimization, power system optimization, TVPA was applied for designing and optimizing an isolated energy system, like battery system and wind battery system, and optimum sizing of hydrogen generator and storage tank. In addition, there are also electricity system cascade analysis, which is not part of it's not, it's part of this subject, it's not part of the scope, but there are electricity system cascade analysis developed for distributed energy generation system design involving intermittent biomass power generator system. You can also say this is a multi-objective linear programming. Okay, this is more toward application in several other countries. If you refer to page 102 of the paper, so far before this next new method, there are other methods. This case in 2015, the optimized by gas plant option using network flow programming approach, considering power demand or mass stability system engineer. But this approach is complex, it's not user friendly. Later you see DVPAs, you can calculate like using normal calculator and sheet of Excel. On the other hand, DVPA could be a simpler alternative for facilitating the development of decentralized biogas system, which originated from the WTA for interpreting renewable heat energy system is yet to be extended. For the design of biogas distributed generation system, serving hybrid demand type that require different biogas qualities. So to address this gap, this is why the auto introduced TVPA methodology for the gas system cascading analysis or gas car framework, targeting supply demand of biogas energy system, determining optimal capacity of energy registered, and biogas storage, so determining uh, the second point. Eh, no, The second paragraph in page 103. Say here, determining optimal fasting energy equivalent of anaerobic digestion reduces. That is the focus of this paper or Geska in this paper. They want to to identify what is the net generation that they should go for. Otherwise, it just they they cannot really utilize all of it. They really need to just use it. We don't want to over design. It's the correct word. Over design the gas generation. Um, yeah. So examining the effect of total well gas demand and supply variation on biogas system sizing and regional feedstock selection. Right. So now, not yet methodology, but section 2, biogas energy system configuration. Need to understand first the abbreviation or symbol in this paper. So how you need to check the paper? Yeah, this one. So, so figure 2, this is figure 2. This is the superstructure of biogas system, energy system considered in this optimization framework, illustrated to show the overall system operational scenario for each time slice T. It consists of AD stand for anaerobic digester that convert different biomass feedstock into raw biogas. The biogas stream produces distant channel into an intermediate biogas storage system. It is included in the configuration together for the possible biogas resource accumulation attributed to the fluctuation in biogas demand environmental demand of final application. So biogas storage system T, T minus 1, T plus 1. So T within T, there are several processes. In addition, purification processing stage GPG is also incorporated in the system to upgrade the biogas into biogas feedstock of higher purity level. Uh, yes. This biogas resource are then fed to satisfy the final application Z, which require different biogas purity level K, which is talking about this part. Here, diesel KT. The diesel KT stand for stand for the demand. The demand. Yeah, for the demand in electricity, demand for NGV, and demand in cooking gas, plus energy content, plus energy consumption. So energy content dissolution, DZ50 refer to table 3. This table 3. mm, this table 3. So the DZ50 from the superstructure is coming from here. Unit conversion later, this explain. We have energy content and the energy consumption. There, at each time slice T, there is an inlet biogas stream for biogas production PT and outlet biogas stream channel to meet the biogas demand. Uh, so PT, yeah, so PT, PT, PT is the demand. PT is biogas production. Biogas production PT. Against the net difference between the biogas inlet biogas inlet and outlet stream at each time slice T would going up with the net biogas inventory from the previous time slice T to result in the current net inventory for time slice T. The essence of TVPA is to determine the targeted value, sample minimum installation power generator size based on the time-based energy data via the numerical cascading approach and graphical approach. So this paper proposed MTBPA known as CASCA to target the minimum biogas storage, minimum biogas generation capacity for the anaerobic digester, and biogas charging discharging profile of AD subject to a set of biogas profile, given profile for different biogas purity level. Oh, I think it makes sense. Slowly, So we have look at the figure here. It's a figure 3. So this is figure 3. So figure 3, okay, page 105. Huh? So the overview of GESCA framework is shown in figure 3. So in figure 3, this is what you need to do in order to do a final, in order to start from final initial installation of GESCA to the final GESCA. Starting with the energy demand of actual Z, Requiring biogas purchase level K. So Z is the application, K is the purity level. T is time. This is why DKZ2. Okay. In general, the methodology of GESCA framework start with the data question extraction, section 3.1, followed by the cascade analysis for biogas energy system, section 3.2, the assumption made for optimizing, optimizing, targeting, determining the optimal capacity of energy digester and the digester as follows. So various variation in energy. So this is talking about this. So variation in energy demand trend of various climate application desertification. This paper, it's electricity, cooking gas, and energy demand. Repeat daily. If you refer to table 1, sorry, table 3, it's repeat daily, meaning it's time slice. Excess raw biogas is stored in biogas storage system. This is just an assumption when you do discard framework. The amount of biogas stored at the beginning of the analysis must be equal to the amount of biogas stored at the end of the analysis to ensure stability of the biogas storage system. Energy equivalent to biogas stream of each time size is carried forward. Yeah. Continue. Energy, okay. Number 4, energy equivalent to biogas stream of each time size is carried forward. This one. 5, losses associated with biogas harnessing for fulfilling the energy demand of final application are considered about the loss factors. So for the loss factors, we refer to table 2. There are list of data required. So one of it, yeah, no. This one is. So FAPPL or loss factor. So for the electricity purity level K is biogas. So this engine efficiency is around 35.9% based on this study. NGV, assume no loss 100%. Cooking gas, assume no loss 100%. Next is the energy value change of the biogas stream. Due to the biogas upgrading system is accounted to consider the opposing impact of methane loss and increment of net calorific value via conversion factor. Still in table 2, so for table 2 of F upgrade, this is it here, F upgrade. So for F upgrade, pro biogas, no loss 100%, upgraded biogas, the biogas killing loss factor 95.2%. Later, we see how does we use this data to calculate the analysis. Number 7, assumption 7, losses during charging and discharging at biogas storage plant are negligible. Leakage of biogas at the compressor is neglected. Leakage of biogas at the transmission line is neglected. Fluctuation in the ambient temperature of the biogas storage system is negligible. The biomass feedstock are being fed into an organizer in a regular and controlled manner to ensure the constant supply of biogas. And there is no variation in the performance of biogas upgrading and purification unit operation. So shown in figure 3, Gasca framework shall involve raw data collection, derivation of total raw biogas demand for each time/P based on the final application energy demand iterative scheme of biogas generation capacity determination through recording the cascade analysis. The target for the biogas generation capacity, biogas storage capacity, and charging discharging the kind of biogas. Okay, now it's 3.2 under methodology. This is the cascade analysis for biogas energy system. So for the assumption here, you need this data for the assumption to do the analysis in cascade analysis. Once all the raw data, okay. So the step for constructing cascadable as follow and genetic cascading procedure is shown in figure 4. This is figure 4. So that is the first. Figure 4. Alright. Okay, genetic cascading procedure for Vesca. So the cascading occurs at the 1, 2, 3, 4, 5, 6, 6, 7 at the cumulative energy QT. You just, if you start with 0, then just 27, so QT1, the same value as this to combine. If you only have QT1, it's here, it's QT1 equal to 31. How about if this value goes to the discharging, meaning we need to subtract the value to report QT2. Iteration to determine new Arabic gestation AT system capacity. So GT new equal to GT all minus QT final minus Q initial over T. Mm, the next one is the cascading. So in order to calculate the GT new here, because the GT gas generation we don't know the actual value. So normal for this paper they just choose one value, reasonably reasonable value, 5,400. They do the optimization, then they reevaluate the GT how using this equation GT all minus Q final minus Q initial over T. So conversion criterion is Q initial must be equal to Q final. If you have 8,000 as a Q initial, so your Q final should be 8,000 as well. Alright. Energy equivalent of total raw gas T for each time slice T is calculated through a series of steps as follows. Alright, wait. The second is still a long way. As to understand this paper, it's worth it to understand it. So energy equivalent of total raw gas demand LT for each time slice T. So LT is the total gas demand. So the total gas demand meaning we cannot just take one value from the electricity or the demand for electricity. We need to add up. In this case, for this paper, it should be demand from the electricity, from the cooking gas, and the NGV. But if you refer to table 3 there are no value for the demand other than electricity. It will start at week 7, yeah, week 7. Yeah, week 7. Then we have demand for NGV and cooking gas. Oh. Firstly, the energy equivalent of the biogas feedstock with different purity level K, FPKT, is 1, is equal to DZKT demand over FLPPL. Okay. Wait. Okay. FPKT equal to DKZT over FAPPL. So APPL here refer to the loss factor coming from table 2. How about DZKT? DZKT is a demand. So the demand coming from table 3. See the derivation of energy demand for each application from raw data. So we have time slice T in this table 3. So each column have its own demand. Yeah, it is DZKT. Where FAPL or KZ is the conversion vector to account for the energy losses associated with different applications. The energy equivalent of raw biogas requirement. So in order to do gas car, you need to have one table for the demand. Once you have the demand table, you need to prepare a derivation of energy equivalent of raw biogas demand for each application, which is what we are currently doing now. We have FPKT. What else we have? Next is the FAPPN. This is the loss factor. This is the demand. And FK update. The energy equivalent of raw biogas required. Operation of biogas system liquidity level KFP rho is calculated using equation 2. Equation. With energy variation due to upgrading process being accounted by conversion factor F upgrade, the conversion factor become unity for direct raw biogas application. So the FPKT is coming from equation 1, but F upgrade is coming from table 2. So for table 2, you can refer to the upgrading average upgrading loss factor F upgrade. We have for raw biogas, upgraded biogas. So for raw biogas is 100% no loss, but for the upgraded biogas there are some loss, 25.2%. So once you have this value, FP raw, so transfer the value to table 4. Select a table. Next is the energy equivalent of total raw biogas demand, LT, is equal in equation summation FP rho. So FP rho, let me do. If you FP rho. So for the for the FP rho here, the value for demand in NGV cooking gas is none. Yeah. So your LT is 263. So if they are sum, this case times less 4, yeah? So you sum up to 160 plus 2626, yeah? 26, so 50, or 732. See, so 732. Wait, check. Really. Sorry. Right. Still very sleepy. It's okay, no? Coffee. So LT, so LT, this LT is the summation of FP rows. So meaning in times plus 7 here, we have 3 FP rows for all of the demand. Alright. So once you calculate the LT, you need to transfer it to the first, sorry, second column of the cascade. The first one you have time slash T, second one is the LT. Next is the number 3. So number 3. The anaerobic digester capacity GT is arbitrarily adjusted and assumed to be constant in each time slice T. These values are arranged accordingly in column 3. So in column 3 means here, in table 3, in table 5, this one. So this is what I'm saying to you, uh, the changes, the optimization is occurring here, gas generation, which will let's see, affect all of the column afterward. Right. So yes, if the net gas energy NT is calculated using equation 4, equation arranged accordingly in column 4. Column 4. So NT is equal to GT minus LT. GT minus L. Column 4 is 1. So GT was 5,400 minus 2633. You get 2766. This is considered for cascade. For 3.5. So we fill up each column in table 4. So next is the charging and discharging gas energy value derived from the values in column 4 as on the sign indication. So if the net gas demand NT is a positive value, the charging gas energy CT is calculated using equation 5 in arrangement column 5. So for charging, it's CT equal to NT FCHG. So FCHG is efficiency of charging at biogas storage. So FCHG refer to table 2. So refer to table 2, the last row. Last row. This row. So both is 100%. So doesn't really matter whether you divide or multiply, it's same. So for this case in this study, the FCHG and FDSCHG or discharge is 100%. So meaning it should be something number like CT equal to NT, NT is the GT minus LT times this value. So for discharging energy, it's division, no? 20 over something. If you check the table 4 there, it's actually the same value. Like, see, 766 multiplied by 1, it's 766. But this discharging, 3709 divided by 1. So, number 6. Effective gas energy at time slice t is calculated using equation 7 and arranged accordingly in column 7. All right, this is the cascading. The cascading in figure 4, this is the cascading. It shall be noted that the infeasible cascading is first conducted assuming zero inventory at the beginning of time period to determine the most effective inventory. Second cascading is then conducted with this value placed as initial inventory. Each time inventory Q initial and final inventory Q final are determined. All right. So let's see here. So for Q initial here, because we haven't done the pinch yet, yeah. So it's 0. So this is the initial iteration. So 0. 0 plus 2766 is 2766. So 2766. Wait. 50, sorry, 50. So 2766, then 2766. This is a new cumulative image. This is the cumulative energy QT, which fall under equation 7. QT equal to QT minus 1 plus CT plus DT. So QT plus CT plus DT. But DT is negative. In this paper, they don't use negative, they use like this bracket. Bracket. So 11,000 minus 2709 will get 7064 and cascading it until the end. Okay. Number 7. Done with the column 7, which is the cumulative energy. It shall be noted the percentage change P is the initial final inventory is going to equation 8. This is equation 8. So P% equal to Q final minus Q initial over Q initial times 100%. So Q initial, because when at the end of the iteration, meaning you get the pinch, the Q final and must be equal to Q initial. This is for Gesca time-based pinch. Right. So for this case, Q final is sorry. For the initial iteration, the Q final, the Q final is 18,000. Q initial is 0. So 18,000 minus 0 over 0. It's 100%. Okay. All right. Not sure why. This is just to see the changes in P for the for the for the first iteration. This doesn't make sense. Yeah, meaning there are no changes, of course, right? Uh, First initial is 0, final is 15,000. So, yeah, because you cannot divide by 0. It's just not possible. Next is for this is, so calculation of P here is for the second, okay, for the second iteration. Yeah. Meaning once you identify until 18,000, the table 5, then you need to redo it again. How to redo this? What we try to, I guess. Yeah. So if the percentage P is greater than 0.05%, new gas of biogeneration capacity GT new is calculated using equation 9. So if this, so if this value is more than 0.05%, so meaning you need to identify or determine a new biogeneration capacity GT new. GT is GT. This is GT. The third column in which we put our first initial value is 5,400. After that, we cannot just simply put, we need to do this equation. We need to use this equation to identify the new GT. Only the first initial iteration, then we guess. Restricted using whereby Q final is final energy content in column 8. Q initial is initial energy content in column 8. Okay. This is the total period of analysis. And the step 3 to 7 repeated until the percentage P is less than 0.05%. So how long you iterate, which is why we need to use Excel to do it. Yeah, but it can be done using manual calculation. So how long you need to do it until the changes of P, equation 8. Equation 8 here, less than 0.05%. Okay. So that's all for the test tested analysis. Not finished yet. It's just how to repair test tested analysis. So case study. Case study is based on Excel tables. In this section, page 106, in this section, an illustrative case study will be briefly discussed to provide basic understanding about this implementation step and to demonstrate the effectiveness of this cascade technique. In this present case study, the cascade technique is applied for communities within Senai City in Johor, as well as surrounding area in both urban and rural areas. In addition, it is assumed that the size of community consists of 1,000 housing unit within the Senai City. So that's this, where this UTM located, able to show the list of data before you open the analysis. So figure 5 to 7 present the demand of electricity, demand of NGV, and demand of cooking gas. That one is stable. into calculator in that way. This is pretty nice. This utility demand data DKZT were derived from extracted data as shown in table 3. This is the table 3. So in this context, the electricity demand raw data available in kilowatt hour unit were converted into megajoule using unit conversion factor of 3.6 megajoule per kilowatt hour. For NGV demand, hourly NGV consumption data in cubic meter cube were then transferred into energy equivalent assuming NGV energy content of 38.5 megajoule per meter cube. So each so each of the demand have their own unit conversion based on the units we see there. So electricity is normalized to kilowatt, GV to meter cube. So cooking gas is hour. For cooking gas demand estimation, the data regarding fraction of time is in which way? Okay. In which cooking gas was supplied for cooking per household approximated, multiplied with total number of households involved in the case study to determine the hour equivalent quantity of cooking gas applied in times less. So this figure was then converted into energy equivalent assuming constant natural gas consumption for cooking for 10 megajoule per hour. So the energy equivalent raw biogas per requirement for fulfilling the energy demand for all production in both of production in table 4 using equation 1 and 2. The total equivalent raw biogas demand LT was determined using equation 3 and shown in the last column of table 4. So meaning table 3 here, this is the raw data. So but the raw data need to be converted in megajoule, which is why you see in each of the column here different values based on the application. So from this table 3, the author do the analysis or calculation, series of calculation. Then we have this table 4. So meaning the table 4 here is based on data from table 3 and the assumption say in table 2. All right, let's see. So for DZKT, demand of electricity, Okay, you sections I need to fill up my words. Right. Continue. So the dessert critique, dessert critique is. So for the dessert critique here, the dessert critique here is based on table 3. For table 3, the value is the unit conversion, energy content, and normal energy consumption. So let's see it. The first value, the first value for demand in electricity is 900, 720, 1260 to 700. Yeah, this is actually N 1800. If you see the NGV, it started at 71357. How about cooking gas started at times less 4 for 2500? Yes. How about FPKT? In this section, the result obtained for gas system cascade analysis is clinically explained as follows. It comprises of three sections, which is optimal capacity of AD, section 5.1, and sensitivity analysis. Okay, we focus on 5.1 first, the optimal capacity of AD and the biogas storage, which is the pinch, the mass pinch. Okay. Table 5 shows the first iteration using gas car. So before we go further into table 5 here, explain first table, table 4 for FPKT, F0 here we have. So for FPKT, the how to calculate FPKT? Let's see. FPKT is equal to section 3.2, step number 2, energy equivalent of total raw gas demand yeah, energy equivalent of raw gas stock with different to level 3. So FPKT equal to DKZT over FAP equal to FAPPN, conversion factor to account for energy losses associated with different applications. So FPKT for electricity, so the first calculation. So 900 divided by APPL. So APPL here is 0.359. Wow. Mm, 5, 9. So you have here is 1%. Ah, yes. Okay. How about FPKT for NGV and cooking gas? You notice the value for DZKT and FPKT is actually the same because it's divided by 1. If you refer to table 2, okay, refer to table 2, see here, application loss factor, only the electricity have is low value, 0.335.9%. But for NGV and cooking gas, it's the author assume no loss, 100%, meaning that's why the value for this FPKT for demand in NGV and cooking is specifically the same. Next is the FP row. You need to calculate FP row. Why? Because in order to get LT is equal to FP row for each demand. So you need to calculate each. So FP row, go back to section 3.2, step number 2, equation 2. So FP row equal to FPKT over F upgrade. FPKT, so it's here, this one. What is one? F upgrade. So F upgrade is from table 2 as well. So for raw biogas, it's 100% non-loss. For upgraded biogas, gas cleaning loss factor, it's 95%. Let me calculate this. All right. So for the value of F0 here, based on table 2, it's actually using the upgraded biogas. So biogas cleaning loss factor is 95.2%, which is, yeah, should be. Because we don't use raw biogas, we need to treat it with biogas before you supply to the demand here. So next for the last column, it's just total up of the F0 for each team. All right, so now we go to the first initial iteration. For the initial iteration, time cycle is given now. The total gas demand LT is what you calculated in table 4. Then the gas generation, this one, gas generation, we assume first we guess the net gas energy NT. So for NT, where you get NT is basically go to section 3.2 step 4. So NT equal to GT minus LT. So T is equal to GT minus LT, then you get NT. So for the negative value, you put bracket. See, 5,000 minus 9,109, 9,109. So it's a deficit. It's a deficit of 3,709.49. Next is the charging energy and discharging energy. So refer to step number 5. To step number 5. So for the charging, this one charging CT is equal to NT multiply with FCHG. 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 So FCHG referred to uh, for this value. For this work, it's This one actually. So no changes whatsoever for the CT but you need to know it doesn't necessarily will be the same value with the NT because there are some calculation involved with CT and DT. For example, CT equal to NT multiply with FCHG or F charging or what DT is equal to NT division over F discharge. Next is the QT. So for the QT here, basically using the value. Before we go to QT, based on the analysis at initial bit digest the biogas generation capacity of 1,400 megajoule per hour. The capacity of biogas storage, think on the paper, page 109, the capacity of biogas storage was determined to be 24,432. Whereas the initial and the final energy content at biogas storage was determined to be 0 and 18,491 megajoule. One is for Q north and Q final. 4,000. 432. Okay, 4,000. Okay. So 24,432 is coming from this new cumulative energy. So based on the initial iteration of this, the capacity of the vehicle is around 24,000. The finding indicate that 18,491, this value of energy must be dumped at the end of daily operation of the cycle to ensure the stability of the industrial system, which is why we need to maximize or optimize the system so that less gas will be dumped at the daily operation. Hence, in order to minimize the wastage of biogas resource via dumping, there would be need to reduce the final energy content Q final by reducing the size of the gas generation GT. So meaning we need to reduce the amount of GT. How to reduce? We refer to equation 9 in section 3.2. From this analysis, two conclusions can be drawn. Firstly, that final biogas energy content is more than its initial amount Q emission, then the AD is oversized. Yeah. If the final biogas content is more than its initial, which is why for gas time-based binge, the Q final and Q initial should be the same. Yeah, because of this statement. If final Q final is more than Q initial means the AD is oversized. On the other hand, yeah, as the sun is undersized. From the calculation, so there should be systematic using equation 5, 7 for the first equation equals 1 to be less than 0.05%. If the percentage change was larger than 0.05%, the calculation would be repeated to determine the new size of the gas station. Not sure how they calculate. Because it's not simple to multiply, isn't it? to divide its root. Hmm. If the percentage change was larger than 0.05%, the calculation would be repeated to determine the new size of the registration capacity. Continue using equation 8, no, should be equation 9. Yeah. Target of 0.05% was set as a tolerance to ensure accuracy of the result. This was also to ensure consistent in daily energy profile of biogas. Storage by dumping the biogas before next day without collecting the biogas. So once the cascading analysis was completed, the optimal biogas station capacity of OD was found to be 4629. So now we go to the, the final iteration. So before you come to this table 6, meaning there are at least 2, 3 iteration. Yeah, meaning we need to recalculate once we change the value of this relationship. We need to recalculate again. Not much to recalculate. It just changes in NT, then you determine the charging, discharging energy to the cascading for the relative with the new value here. And the optimal biogas storage capacity is 16,988. Here, 16,988 is shown in table 6. The targeted initial and final NG content of biogas storage were found to be identical at 737.19 megajoule per hour. As highlighted in table 6, the pinch point occur at time slice 12. Yes, the time of negative energy restore at this storage system at this standard interval. So from the first iteration, we can calculate, let me calculate. We can calculate the new GT using equation 9. Let's see. Uh, so GT new, to GTO. So GTO is 5,400 minus Q final is Q final. 15,400 minus 0 over 24. I'm sorry. One, oh, sorry, 1.1. You got 22, so 5,000 minus, so it was 629. 629. Oh, so it's similar to the, okay. So for this case, only one iteration is enough. Yeah. Because you see the, oh, sorry. So in table 6, the GT reduced to 4629 based on question 9. So need to recalculate all. So we try calculate one first, huh? So NT is equal to GT minus LT. 4629 minus 263. So 1966. Discharging 1966 times 1 is 1966. Oh, but here times less 4. So 4629 minus 472, we get negative 103. And then you do the cascading 1966 plus 2522. Oh, sorry. Yeah, correct. 1966 plus 52. So you get 4518 plus 2576 at 094 or 095 and so on. So this is the first cascading until the end. So the end is 0 then. You see? Next is the a new cumulative energy. So for the new cumulative energy, H373 is coming from the cumulative energy QT based on the largest negative value, which is normally that how we do it. When we try to find the pinch point, we find the largest negative value. So in this case, H737 become the new, become the Q initial now. So for the new cumulative energy, QT new, we do the cascading again. So instead of 0, it's 8737 plus 1996, 10,733, and we do the rest until the end. So the end, you see the value of Q initial and Q final is the same, and there are 0 here. So this one, 6. Hindi lang yan. Wait, wait. Mhm. Oh, okay. So QT new. Okay. 6 plus 252. then 72, 73, yeah, it's 256, okay, understood. So for this calculation, QT is equal to equation 7, QT equal to QT minus 1 plus CT plus DT. Wait, this is wrong. Yes. Mm, that's not it. That's what I want. Mm, mm, okay. So, right. So QT here, so QT here is actually QT equal to this value plus this value and this value. So you get this value. Uh, yeah. 1996 plus 2522 plus dt, which is no value, you get at 095. Let's see. Plus. Alah, alah. Hmm, alah, ah, the so 106.15 plus 2552.83. So you get 4518.98. So for this QT new here, it's actually at 737 plus 19915. Not 199 this one. It should be plus this number. Then you get this number. How about 10733 here? 10733 plus with this value. Then you get the 10733.34 plus 2522.83, 13256, 13256.17. Yeah. So this value, it's either, meaning if it's dt, then you need to minus dt. So straight with dt. For charging energy CT, it's summation plus. All right. So do the rest, which is why at 3098 here, you see here, 0.8. Oops, sorry. So 3098 minus 3098, you get the pinch. So, so you need to do once on this. Alternatively, graphical. So the targeted initial and final energy content of gas storage were found to be identical at 77.1 megajoule per hour, as highlighted in table 6. The pinch point occurred at the time SAS 12, implying no cumulative energy was stored at gas storage system at this time interval. Hmm. Alternatively, graphical analysis can also be applied to perform the targeting of decentralized gas energy system. Figure 8 shows the graphical pinch analysis principle to produce demand-supply composite curve. Based on the graph, the targeted gas generation capacity for AD was 469.52 megajoule per hour. Inverse gradient of the supply graph, whereas the targeted gas storage capacity was 16,988. Maximum horizontal difference between demand and supply curve. What is this curve? Okay, figure 8. This figure 8. Figure 8. Okay, so figure 8. It showed that initial final energy content were the same as absolutely at 737. At 737. Ancestor is here, page point. Uh, 727. Show the final energy, initial and final energy content. At 727. So here, the distance from 0 to green line there is actually at 737. So from this blue line to the end of the green line, the value here is at 737. Should be similar to the new emission. Pinch point occurs at time slash level. So where the demand and supply curves touch each other. This is the supply capacitor. This is the demand capacitor. This implied that the energy was zero and the combination of respect by the storage that obtained from the electronic person system with the miracle approach of this car. To the illustrate the electrical division on energy in the storage. Okay. So targeted targeted gas generation capacity equal to inverse gradient supply graph equal to 469.54 megajoule per hour. So this value is actually GT. Yeah. So how you get this composite curve? You already determined the value here, 737. So you create a line tangent to the demand composite curve until it's in line with the demand composite curve. So this value and this value should be similar. Energy and J. So how about the cumulative energy? Sure, why something 110,000? 0.6, 0.9, 2766, 6 plus 518, 6514 plus 8095, 8095 is 196 should be the 6514. Changes. It doesn't say how we come up with the figure 8 here, especially the x-axis. Is it based on the total gas demand or the net gas demand? 1, 2, 3, 1, 2, 3. 1, 2, 3. Then we have the negative. Have negative, positive, positive, negative. Okay, we can now. So for this point here is based on the NT, start with 1966, so 1966 plus is a quality, so plus 2522 plus, so we have 4518, then plus 3576, we have 8094, yeah, plus 103 because it's cumulative, 22, but the negative We have different, how is it, symbols with X, yeah, and accumulating all of it, it can reach up to 10,000, maybe, not sure. Okay, yes. So we have this graph. This is the graph energy profile in biogas storage. Pinch point at times less to Earth. Initial and final gas storage is the same. The source of animal manure and comey. This is a line. One U. This is the UTM. So we have palm oil, dairy farm again, Punai farm within there. It's a nine. Okay. Okay. So section 4.2 source of feedstock. This is not really part of the cascade, but it's just it's a case study. Need to know it. So figure 10 illustrates relative. This is figure 10. Relative location of palm oil mill industry and dairy farm within the maximum covered radius of 20 kilometers away from the city. Table 7 shows detail of household and dairy farm and palm oil mill for the case study. Table 8 shows the biogas potential produced from the available feedstock. So this is the table. Table 7 is the dairy farm amount of dairy farm housing and dairy farm. Sorry, palm oil mill. Level 8 is the biogas potential from different feedstock with respect to distance from Sunrise City. The basis of biogas participation for each feedstock is presented in table 9. So to get value for table 8, we refer to table 9. Basis on sample population of food waste, feedstock, and biogas zone 1. So potential value. Household waste generated kilogram per pack per day, 0.34. Vegetable per household is for, okay. As shown in table 8, zone 3 and 4 have higher total biogas. Mm, Potential, volume 5, which is 5315 and 10,274 due to collective biogas consumption with waste, animal manure, and farming. For the last one column, that biogas zone 1 and then 1 to 2 have sufficient biogas supply to fulfill targeted mm, targeted biogas to positive value of the zone was higher than compared to total biogas production and only zone 3 and 4 have enough supply to meet the targeted biogas demand estimated from gas card. So, value for this value, 10,274 minus 469. For 629 is the net generation of gas GT. Right, yes. Okay. Minus, uh, uh, then we get this. So 460, because this is not that much, so it's a positive value. Okay. It's plus the same. Yes. In order to examine the effect of demand variation requirement of physical capacity of anaerobic digester, three scenarios are presented in table 12. The, in the first scenario, when the demand profile increased by 20%, the scenario, from the baseline, the targeted gas would increase from 4,629 to 555.2. So 4,629 is the net gas generation based on the gas car analysis. So increasing by 20% of the demand would increase the net gas generation up to 555.42. So due to this, Zone 3 and Zone 4 had enough biogas supply to meet the targeted scenario in scenario 1. Similarly, when the demand was decreased by 20%, the targeted value also decreased from 469 to 3702. Due to this, Zone 3 and 4 had enough biogas supply to however, both initial energy container similarly level of biogas remain unchanged, distributed to the same demand of 100 plus times less. Okay, 5.3. The introduction of biogas system has encouraged the application of biogas in community, therefore reduced the carbon emissions since biogas combustion is carbon neutral. The carbon emission avoidance attributed to biogas application for zone 1 to 4 is calculated in this section to examine its positive impact. The parental use proportion are summarized in table 13. Okay. Is the reference where they get the value? More specifically, carbon emission avoidance through biogas energy system is due to substitution of conventional fuels, fossil fuel, and avoidance of methane generation from natural decomposition of biomass feedstock. The carbon emission due to fuel application for fulfilling electricity, natural gas vehicle, and cooking gas demand is predicted as in table 14. Fulfilling this energy demand using biogas energy system would avoid carbon emission by 87.9.43 CO2 equivalent. Yeah, this one. So this value 0.89 coming from the table 13 factor. So this value is coming from this factor. Like US EPA, we have IPCC. So just finish it. Moreover, it was found that biogas capture from anaerobic treatment of food waste and manure from home feedstock had led to methane emission avoidance up to 129,345 129,345 kilograms CO2 equivalent per day as shown in table 15. Table 15. This is methane emission. So methane emission value coming from this table as well. So methane emission is coming from the food waste and manure compound. Overall application of the proposed AD energy system is susceptible with emission of 13809 kilograms CO2. So this value plus this value, you get 138,094 kilogram CO2 equivalent per day. Okay. So that is discussed based on time base. Yeah. You can do this example first. Exercise. Let's see it. 5 minutes, just roughly. So, what we need to do is we have the LT there. So your task is to prepare what else? Other column after that, static people gas generation GT. In this case, GT is given as 7,000 megajoule. So for final exam, you study this section topic. So next is the NT, net NT, net gas energy, column number 4. Gas generation is zero, just calculate. Okay, next, net gas generation is GT minus LT. So 7,000 minus 2633. You get NT. Next is the charging energy, discharging energy. That one for this case, it's divide by 1 or multiply by 1. Depend on the charging or discharging. Then the cumulative energy is QT equal to QT minus 1 plus CT plus DT. So you do the cascading. Once you finish cascading, then you need to create a new cumulative energy. But if you create new cumulative energy, it should be the same because this is the high initial iteration. Yeah. So from this, you need what you need to know is actually the Q initial execution is zero. You need Q final. So the Q final is used to calculate the new GT. Mean GT new using the equation equation 9. I forgot this number there. Equation 8. So once we have this final iteration, so let's see, we try to calculate the P. P for equation 8. The changes, because the changes in P should be, let's see, less than 0.05%. So P% P equal to Q final is 8737. Oh, should be kosong lah. Oh, 737. 107. Thank you. Yeah. Zero, zero divided by a very large number, zero. So it is zero then, sorry, it is less than 0.05%. No. So next was to get the cumulative. This is for initial iteration. We need to prepare to get the new GT. So the new GT will be used for the next iteration. So you do once you get the GT, you need to recalculate the net energy and the charging, discharging, DCT, and DT. Then you get a new cumulative, right? New cumulative energy. So from the new cumulative energy, you need to calculate sorry. From the cumulative energy for the second iteration, you need to calculate a new cumulative energy with the of Q naught of the value from the all the cumulative energy, the previous column. So the Q naught have should be the largest negative value in the previous cumulative. That one you can refer to table 6. Then you need to recalculate the QT is equal to QT equal to QT T minus 1 plus CT plus DT. Yeah. Then you get this new calculate, you will get the pinch at the largest negative value in the all negative energy, which is the pinch. And you will see the Q naught and Q final is the same with. I'm not sure about this exercise. How many iterations that we needed? Normally it's take 2 or 3 iterations. For this paper is only one. Only 2 iterations, including the initial one. Okay. So, any question so far for this so that's all for my part. Yeah. What we have learned so far is we you have learned about water cascade analysis, which is it's not really the idea is the same to the cascading, but the way we implement is not the same with the gas cascade analysis. So we learn about gas cascade analysis for the hydrogen, for the nitrogen, oxygen. Actually, it's the same regardless of the cases. Then today we then you think this is based on multiple objective because we have demand from several applications. So to fulfill the demand, we need this why it's called the objective. And study this part for this topic for your final exam. I'll prepare one question. Still have 10 minutes. You have any question, you can ask. Yeah, actually, it's a lot. Yeah, I have a thought about do people water different objective for water cascade analysis. That one is different. But, all right, so thank you. So see you again during the final exam and do the invigilator. Later, Hari, the best with the project.
Thank you so much, Doctor.
All right.
Thank you, Doctor. Bye.
Thank you,
Doctor, just untuk confirmation, Gaskar jangan masuk, huh?
Oh,
Okay, alright. Thank you so much, Doctor. Okay, alright.
tapi ada sikit ke question from Dr. Asrul. I'm not sure which one.
I see.
My
So,
kid is just,
part Doctor take based on case study yang kita share tak lah, huh?
time based.
Okay, right. Thank you so much. Assalamualaikum.
Yeah.
By the way, Doctor minta recorded lecture boleh?
Oh, stop lah. Oh,
Okay,
Okay.
alright.